Okay, welcome back, everybody. So, the end of lecture yesterday, we ended with nice closed form expression for these Catalan numbers, which, remember, our interpretation of this was the number of ways to group k plus 1 matrices multiplied together. So using associativity of matrices, that grouping could be done in C sub k number of ways. Again, this k plus 1 matrices here. Um, this was our original motivation for computing these numbers. Anyway, through that consideration, we found these are exactly those numbers that count this situation. So I mentioned that these are, the second most frequently appearing numbers in combinatorial applications after the binomial coefficients. Of course, you might raise your hand and argue that, well, these themselves involve the binomial coefficients. True enough, but um, in particular, like the Catalan numbers appear in many, many, many different contexts. So, as I mentioned yesterday, um, you can look up many for yourself. There's one of these that I wanted to pick out in particular, though, and that's the following. So, going to define a rooted tree. So a rooted tree is a tree with a distinguished vertex called the root. Okay. So a rooted tree has a root, has a vertex that is special among the vertices. The vertices in a rooted tree form a hierarchy of sorts. How so? We can take the root as the highest level. And all other vertices place in this hierarchy is determined by their distance to the root. Okay, so vertices that are closer to the root than others would be higher in this hierarchy. In fact, a way of classifying this with some terminology is as follows. So if V and W are, we'll say, adjacent vertices, in a rooted tree, and if V is closer to the root than W, we say V is the parent of W V is the parent of W, and W is the child of V. Okay. We could also define siblings, grandparents, cousins, other family relationships you might want to talk about in a rooted tree. So it can also define siblings, uh, grandparents, cousins, etc. Okay. One more definition. We say a rooted tree is strictly binary if every parent vertex has exactly two children. Okay. So we say that a rooted tree is strictly binary if every parent vertex has exactly two children. Okay. Question. How many strictly binary trees are there with k parent vertices? The answer is this many. The Catalan numbers. So, to see this, we note a way to associate a given uh, strictly binary tree. Remember, a strictly binary tree by definition is a rooted tree, so I don't need to say a strictly binary rooted tree. Strictly binary tree is already a rooted tree because we need the root to be able to talk about parent vertices in the first place. So to see this, we note a way to associate a given strictly binary tree with k parent vertices to a way to multiply k plus 1 matrices in a unique way. This assignment is unique, is what I mean. Okay. So the examples here, let's do the following. Let's say I'm doing this for 4 parent vertices. Okay. So let's say I'm doing this for 4 parent vertices. What does my strictly binary tree look like? Well, I'm going to just pick one. So I'm going to have root here and 2 children. And then this one is going to have 2 children. And then this one is going to have 2 children. And that is that. So here are my 4 parent vertices here. Okay. So, let's, where, actually, hold on. I didn't draw 4 parent vertices, I drew 3. Oh, yeah, this is fine. Yeah, this is fine. Okay. So, let me correct this. 3 parent vertices. I could have done it for 4 by adding adding 2 more children, but I'm not going to do that. So yeah, the 3 parent vertices is fine. We'll just do it in this case. Um, so I have 3 parent vertices here. There they are. Okay. Now it can be shown that if I have k parent vertices, uh, here's a quick question. Let's say that I have strictly binary tree. K parent vertices. How many leaves? How many leaves do I have? I have strictly binary tree. I have k parent vertices. How many leaves do I have? Here's one with 3 parent vertices. I have 1, 2, 3, 4 leaves. I wonder if that's always going to be the case, though. Well, it is, in fact. This is k plus 1 leaves. This isn't in your recent homework, but it will be in your next. This is exercise 2 in this section. Okay. So there's always k plus 1 leaves. So in this case, there are 3 plus 1, that is 4 leaves. Label them from left to right. X0, X1, X2, X3. So X0 to XK. Okay. Here, because K is equal to 3, this one's X0, this is X1, this is X2, and this is X3. Now, my claim is that this determines a grouping of the 4 matrices. So the claim, this denotes a grouping of the matrix product that unambiguously, because the associativity rule can be written like this. But when I'm interested in what order I'm doing these operations in, of course, this suggests a grouping. How does this suggest a grouping? Because x0 and x1 are children of this vertex, they are grouped together, and then we go up the tree toward the root. So this would be x0 and x1 grouped together, and then grouped with x2, and then x3 is the last one. So this strictly binary rooted tree, we label it like this. This is associated with this grouping of the matrix product. Let's do another. Also with 3 parent vertices to see how this works. So There we go. So the three parent vertices are here, here, and here. Okay, let's do the same thing that we did before. We're labeling them from left to right, x0, x1, x2, x3. What are we labeling? We're labeling the leaves. And I claim because we have three parent vertices, we always have 3 plus 1, that is k plus 1 leaves. This gives us k plus 1 matrices here with this labeling. And I claim that this one, what kind of grouping of the matrix product x0 times x1 times x2 times x3 do I get from this strictly binary tree? Well, now x1 and x2 are going to be grouped together, then x0 grouped on the left, and then x3 grouped at the end. So this would be the multiplication x1 and x2 grouped together, then grouped with x0, then x3. Let's do one more to really nail this down. So let's say my three parent vertices are these three, so I just need two more of these. There we go. All right. If I had given you the pen and asked you to draw a strictly binary tree, this is probably like the first thing you would have drawn. Okay. Again, let's follow this. Let's label. What grouping does this correspond to? Well, grouping x0 and x1 and x2 and x3. So this explains how these strictly binary rooted trees can be seen to be counted by the same Catalan numbers, because this means is that the number of strictly binary trees with k parent vertices is equal to the number of ways to group a product of k plus 1 matrices, which is, of course, the Catalan numbers. All right. So this is the application of the Catalan numbers that I thought maybe if the matrix multiplication groupings didn't grab your interest, maybe this one would. We can see that those are equivalent formulations of the thing you're counting, but nevertheless, maybe for whatever reason you're more interested in this way of thinking about it than just dealing with the matrices. The matrix way of dealing with it is particularly nice because you can just straight up see the recurrence relation. Even though it's a nonlinear recurrence relation, we could just straight up see it, and that was important for us. Okay. So this coming at this from the computer science angle, of course, you might not be that unfamiliar with using these strictly binary trees in this fashion to designate order of evaluation of arithmetic operations or expressions. So maybe that was like the most obvious treatment of it possible to you, and in which case, good. That's good. It's a good thing. So now, how do I? This is a very general question. So now this is something different. Let's see. How do I count the number of some arrangement when there Is symmetry present? This is a different thing than if you're talking about like whether you're distinguishing like the order or not of what's going on. This is not always exactly the same consideration, right? If you think of like drawing like red, blue, and white balls from a bin, each containing some number, the bin contains some number of each type of ball, but all the balls are identical. You can't distinguish them. Um, so they're not like numbered or anything. You don't care what order you drew them. You just care like the actual numbers of types. Um, these questions can be related, but also are not always the same sort of thing. This is not really what we're talking about when you're talking about when symmetry is present. So what do we mean? Here's some examples. Okay, so how many ways can King Arthur and his knights sit at the round table? So how many ways can King Arthur and his knights sit at the round table? Of course, the round table is round, we hope, and we mean by that that it is perfectly round, so there is no way to distinguish position, right? What we mean by this, of course, is that if here is the round table, and we start and we say put Arthur here, and then maybe we put Gawain, Percival, Bedivere, Tristram, and so on in this fashion. Well, could I distinguish between this configuration and this configuration? And the answer is no, because there is this symmetry. This is a round table. So this ordering that I'm given, yeah, I didn't fill it out, whatever, right? I'm just filling out a part of it and say that I've fixed whatever the remaining people sitting at the table are. They're in fixed order from here. If I look instead at this order where, yeah, okay, maybe Arthur is at the top of the table here, but that's, again, what direction am I facing in the room, right? Like, if I'm hanging in the top of the room looking straight down at the table, what's my initial orientation, right? Did someone spin me first? Like, I don't know what position how I'm oriented here, so there is no top position. This isn't necessarily the North Pole, right? So the point is that there's no distinguishing between these positions because this ordering is exactly the same. These two configurations would be the same. So there is some symmetry here. There's no distinguished position at the round table, so doing this clockwise will be the same, right? I have the same ordering clockwise, and those would be the same. These were the same configuration. Okay. Another question. How many different necklaces within beads can be formed using M different types of beads? Now we'll explain that these M types of beads are identical. We'll say that the different types, each type is indistinguishable from each other. From others of the same type. So maybe the type of bead refers to the color. In that case, say all red beads would be identical. There'd be no way to tell two red beads apart. Or if these were glass beads, all the glass beads would be identical. Whatever word, whatever characterization of the beads, they are identical within their own class. Okay. Why is this a question that is maybe a little bit hard to think about? Well, there is again some symmetry here, right? So the symmetry that's present in Arthur's case was obvious because of the roundness of the table. Here with this necklace, where is the symmetry coming in? Well, we would say that two necklaces are the same, similar, the same, equal. Two necklaces are the same if we can transform one into the other by either rotating the necklace or flipping it, turning it over. So if we could transform one into another by, I should say not another, the other, since I'm specifying two necklaces here. So we can transform one into the other by rotating or turning it over. So the rotating bit we actually saw up here with Arthur in the round table. So let's see an example of this with a necklace. Let's say I've strung together a necklace and I have maybe this is what it looks like. And these vertices are the beads. Let's say that this is a red bead, this is a blue bead, this is a red bead, and this is a green bead. Okay. So I could rotate this by, I'm going to rotate this by sending this vertex here, this vertex here, this vertex here, this vertex here. So this would be G, then this would be R, then this would be B, and this would be R. Right? And so this would be the same as this because it's just rotation. But also, I can flip this. I can flip the necklace over. So think about this as an actual necklace with these beads laying in front of you, and you take it and you just flip it. Instead, if you do that, then this necklace looks the same in terms of that, but what about the colors? If I'm flipping it, I'm going to flip it this way, right? I'm going to flip it this way. So red goes here. These two are inner swapped. These two are inner swapped. So this would be B, R, and this would be R, G. So all of these would be the same necklace. Okay, so there's even more symmetry present here. Okay. Now, to answer these questions, we need the notion of a mathematical group. So when we say group, it has a special meaning here. So we need the notion of a mathematical group, which is the topic of the subject of math known as group theory. I can't possibly explain to you like all of the ways that groups are important in everything from solving a Rubik's cube to physics of all kinds, theoretical physics especially, but physics of all kinds, to many, many, many fields of math, whether you're doing geometry, algebra, analysis, whatever it is you're doing, groups show up somewhere. They are an extremely natural object, as we're going to see. They come about very naturally. This won't feel super inorganic to do it this way. But groups are very, very, very important. In fact, you have already, whether you know it or not, been dealing with groups for a large chunk of your mathematical career. So, for instance, matrices all taken together with a special condition here, they're form groups. The integers are a group in a couple of ways. So we'll talk about all these things. But first, what is a group? And why do they show up here? Groups tend to show up in situations where symmetry plays an important role. So it's natural that in these questions that I asked, these would show up, since that was exactly the deal. Trying to distinguish between the number of ways we can do these things. Here's my examples again. You can see how the symmetry plays a big role, because that is going to determine which things get counted as the same and which get counted as different objects. If I don't fully understand that, then how could I possibly hope to count the number of distinct such objects, right? So, how does this go? What is a group? A group, G, consists of a set. Maybe I should call the set G. So that's what I'll do. Even though we're going to, very quickly, we're going to pass from this way of talking about it. And when we talk about a group, we are going to just mention a G, the set that it's on. Usually the operation involved will be obvious. A group consists of a set G together with a binary operation that we'll call star. Okay, defined on G such that we have a few properties this has to satisfy. So one, closure. It is closed with respect to this operation. So two elements A and B are in G. That means that whatever this element is that I've defined using this binary operation, this also has to be in G. So you take any two elements, you combine them with this binary operation. A star B has to also be an element of G. Okay, it doesn't take you out of the set of G. It has to be associative. So if A, B, and C are in G, this means that A star B star C is the same as A star B star C. So it satisfies the associative rule, the associative property. From this, you can prove generalized associativity for any number of products, any number of terms in your product, not just three. Use induction to do that if you want. Okay. Thirdly, must have an identity element. So what does this mean? There exists an element, we'll say E, in G, such that E star A is equal to A star E, in both cases equal to A for every A in G. We call this E the identity element of G with respect to this operation star. So we say E is the identity element of G with respect to the binary operation star. This identity element, of course, is acting like 1 for multiplication, right? Or 0 for addition. If you don't quite understand what I'm said there, then it's fine. We're going to do a more drawn out example of these things. And lastly, inverses. And this is for every element A of G, there exists an element B in G such that A star B is equal to B star A, which is equal to the identity. B is called the inverse of A and is written B is A inverse. So there exists this identity element. Okay. All right. What are some examples? Let G be the set of all 3 by 3 matrices with non-zero determinant and real coefficients. Let star be matrix multiplication. Then the set G together with this binary operation star is a group. Let's just check all of the requirements. Closure. If I have two matrices, two 3 by 3 matrices, non-zero determinant, and I multiply them together, this is going to be a 3 by 3 matrix with non-zero determinant because, as you might remember, the determinant of a matrix product is the product of determinants. This is one of the most important properties of the determinant, is that it works this way. So this tells us that if each of these are non-zero, this is also going to be non-zero. So I go to multiply two matrices. Multiplying two 3 by 3 matrices gives us a 3 by 3 matrix. It's going to have non-zero determinant if each of those do. So I started with two 3 by 3 matrices with non-zero determinant real coefficients. I multiply them together. I get a 3 by 3 matrix with real coefficients and non-zero determinant. So it's closed. 2, associativity. Matrix multiplication is associative. We better hope it is, right? Because of course we our discussion of the Catalan numbers talked about how to group k plus 1 matrices multiplied together using the generalized associative property. Okay, so it's associative. 3, I have the identity element. Well, with respect to matrix multiplication, the identity element for 3 by 3 matrices with real coefficients is exactly this thing. This is NG, and IA is equal to AI is equal to A for all matrices A and G. Right? Because that's how the identity matrix works. Okay, so we got those. What about inverses? If A is in G, then the matrix A inverse exists since A has non-zero determinant. So, yes, this is a group. In fact, this group is called GL3R. Okay. You can notice that absolutely nothing here depended on the 3 by 3. This could have been an n by n. It would have been exactly the same. In fact, we only reference the size like here. Here, if both of these are n by n, then their product is n by n. Nothing else referenced the size of these matrices, so actually this is true for GLNR, the set of n by n matrices with real coefficients with non-zero determinant. Okay, that's what guarantees that the inverse exists. But of course, notice matrix multiplication is not commutative. So in general, in this example, AB is not equal to B times A, i.e., this matrix multiplication operation star, which I use the normal notation for matrix multiplication here, but I could have put stars in between here and just say that's what I'm doing. Star is not commutative in this case. So it's a special case when the binary operation is commutative. So here's another definition. If a group set G taken together with binary operation star is satisfies that A star B is equal to B star A for all A, B, and G. This is to say that this binary operation star is commutative. In this case, we say G is an abelian group. So an abelian group is one for which the binary operation is commutative. Okay, so these matrix groups, of course, are going to fail that in many instances. Let's see some other examples before moving on. Let's do the set of integers with addition. So z is all the integers. I think I've written it like this in this course, but this z comes from the German Zahlen for number. Star, or even I guess it's both. There's the noun like numbers, and there's also Zahlen like to count. I think is the German verb. Maybe I'm wrong. It's been a while, but I think that's the deal. This is the integers, and I'm going to take my binary operation to just be plus, just addition, just normal addition. Okay. Then just a quick check, closure. If a and b are integers, a plus b is also an integer. Closure is something that you're not going to have to worry about typically, because if we're talking about it in context, right, the operation you're going to be talking about is not going to be something that takes you out of the set, but it is technically something you have to think about. But for the most part, it's the other three properties that really define the group. Secondly, associativity. Well, a plus b plus c is equal to a plus b plus c, right, for all integers. So normal addition, integer addition, even addition of real numbers is associative. Do we have an identity element? 0 plus an integer is the same thing as that integer plus 0, which is just the integer itself for all integers. So 0 is the additive identity. It's the identity element for addition. And then lastly, inverses. Well, any integer plus its negative is 0 for all integers, right? So yes, each a has an inverse. So a inverse in this instance is minus a, right? The inverse element is just the negative of that thing. Okay, so all of these are satisfied, and this is a group. Actually, this is even an abelian group. Right? In fact, integer addition is commutative for all integers. Right? So it is an abelian group, even. Okay. Let's maybe do another example. If g is the integers and star is multiplication. So multiplication of integers. Then what do you think? Oh, I should just say multiplication here, but whatever. Is this a group or not? It is not a group. Can you identify what goes wrong here? Hint. 0 has no inverse. Because now the operation is multiplication. 0 has no inverse with respect to this operation. You might raise your hand and say, wait, 0 wasn't a problem up here. Well, yeah, because the operation was addition. 0 has an inverse with respect to addition. It's just 0. Right? So it's just 0. So here, what can I multiply by 0 to make it equal to the identity for this group? Well, what is the identity for multiplication? It's 1. 1 is the identity element for multiplication, right? It's 1 times a that is equal to a for every integer. And so it's the identity element that shows up on the right-hand side in this form. The question is, I'm looking for an element such that 0 times that element is equal to 1, and there exists no such thing. So 0 has no inverse. This is not a group. What if I restricted this to being non-negative integers, we'll say, or not non-negative, we'll say positive integers? And multiplication, is that a group? These are positive integers. The inverse operation here is tricky, right? Finding inverses is tricky. What's the inverse of 2? This also has problems, right? So we even have problems even if we get rid of 0 here. Try the real numbers that are not 0 and multiplication. This is a group. You can also do this with the rationals instead of the reals. You don't actually need the reals here, but this works. Okay. Let's do another example. Okay. So this is maybe the most important example. How about groups of permutations? Well, remember, so recall a permutation of n objects is really a function pi defined on the set 1, 2, so on out to n. Okay, by ordering the objects in some fashion. Then taking pi sub I to be equal to j if the ith object in the ordering occupies the jth position in the permutation. Okay. And so this, we should note a few things here. So note there's a few facts about this object, this permutation. So I'll say this is the first fact. The value of this permutation on I is not equal to the value of this permutation on J if I and J differ. Okay. You might have seen that property before, though. This is saying that this pi is 1 to 1. Another way of saying this is that pi is injective, or pi is an injection, however you want to talk about this. There's another property that such a function has, which is that for every m with m between 1 and n, there exists a number I such that pi of I is equal to m. So something gets moved into that position, right? Something gets moved into the mth position. And so that's just saying this. This is another way, though, of saying that pi is onto, which another synonym for this is surjective. Okay. A function that is both one-to-one and onto is called a bijection. From the set 1 to n to itself. Okay. Thus, every permutation of n objects corresponds to a bijection on that set, and every such bijection corresponds to a permutation. So, bijections on the set one to n, these are in one-to-one correspondence themselves between permutations on n objects. Constructing a bijection between sets is a way of counting sets in the sense that a bijection between two sets in some sense says that those sets have the same count. They have the same cardinality. Okay. Okay. So let S sub n denote the set of all bijections on the set 1, 2, and so on out to n, on the set of n objects. Okay. Let star be function composition. Then this set taken together with this operation forms a group we call the symmetric group on n objects, in letters, however you want to describe it. And we're just going to use S sub n to denote that group. Okay. It looks like a symmetric group on objects here. Symmetric group on n objects. Okay. Or symmetric group on n letters, symmetric group on n elements, however you want to describe it. The way to think about this, so think for a second. I claim that this forms a group. I'm going to leave that as an exercise. So this is exercise 4 in that section. So I claim that this forms a group. I'm not going to fully show that. You are going to do that in homework. But to think about this for a second, what is the identity element going to be? What is the identity element of this symmetric group? We'll call it like pi naught, and it's a pi naught such that pi naught composed with any permutation pi is the same as that permutation composed with pi naught, and both of those have to be equal to pi. And this has to be true for all permutations or bijections pi in this Sn. So what does it? What does this? Turns out that this pi naught is the permutation that sends every object to itself. This is the identity permutation. Let's think about this for a second. So one thing that's always tricky about function composition is that function composition occurs right to left, right? It's you do this thing first, then you do that thing. Then you apply this to it. You do this thing first, then you apply that thing to it. So function composition occurs right to left because of how the notation works. Here, let's think about this for a second. I have a generic permutation here. It does its thing. Whatever thing it did, if I define this identity permutation in this way, that whatever it finds here, it just fixes it. So whatever this did will not be changed by this identity permutation. Similarly, applying the identity permutation first to 1 to n does nothing to it. It leaves it unchanged. Then applying pi to that is just the effect of pi on that thing. So this is clearly the identity permutation. I'll leave it up to you to check those other properties that this is actually satisfied. This forms a group called the symmetric group. Okay. Now, what is the size of this group? When we're talking about groups, we use the same terminology as graphs, so order of the group is what we talk about. You don't have to worry too much about that now. But what is the order of this group, or what is the size of this group? Well, this is the number of permutations on n objects because of this previous correspondence, because permutations on n objects, for every one of those, there's a bijection and vice versa, so these are the same count. So to a bijection is associated permutation and vice versa. So this is really asking how many permutations are there on n objects, but we know that well. That's n factorial. Okay. So in this fashion, even though we've defined this as the set of all bijections, we're going to interchangeably just use the word permutations here, because ultimately there's no difference between those things. Okay. Now, it turns out that to understand permutations, as elements of this group, we need much better notation. We'll call this cycle notation. Okay. So the way that we do this is as follows. Maybe I'll do this on the next page so that I have plenty of room. So this is cycle notation. So cycle notation for permutations. Let's say I have a permutation pi. Okay, so I have permutation pi in my symmetric group. And to specify this, I need to name whatever this is. I need to specify what this pi of k is for each k. So maybe you do this as a table, or maybe you do it as a row like this. So here's 1, here's 2, here's 3, here's 4, and so on out to n. And then you would say, okay, here's pi of 1, here's pi of 2, here's pi of 3, here's pi of 4, and so on. And lastly, here's pi of n. So maybe I do the following, right? So let's do a permutation like this on 5 objects. 1, 2, 3, 4, 5. And then, so I'll send 1 to 3, 2 to 5. I'll send 3 to 1. I'll send 4 to 2. And I'll send 5 to 4. That's specified now. There's nothing else I can do here. Okay. If any of these had repeated, that wouldn't be 1 to 1, right? So, of course, I can't repeat the top row. It wouldn't even be a function there. I couldn't repeat entries in the top row. Now, the way that I would write this in, so this is not cycle notation yet. This is too cumbersome. This is not amenable to computing things. It's too cumbersome. And what this is really, like if we translate this into even more cumbersome form, this would be the following list or table. So, really, what is important here? Let's track what is actually going on. 1 gets sent to 3, and then 3 gets sent back to 1. Which of course gets sent to 3. Like this is like a closed loop almost, right? 1 goes to 3, then 3 goes back to 1. 2 goes to 5, and then 5 gets sent to 4, and 4 gets sent to 2. In a way, thinking of these as 2 cycles, the reason why we use the word cycle here is clear because these cycle around. 1 eventually goes back to 1, 2 eventually goes back to 2. We can think about this permutation as being a combination of these 2 cycles. And the way that we would denote this is the following. This is cycle notation for this permutation. This has the same meaning as this. This is saying what this permutation pi does here. I'm calling this pi. What this permutation does is it sends 1 to 3 and 3 to 1. It sends 2 to 5, 5 to 4, and 4 to 2. So reading left to right, when I get to the end of the parentheses, that means I go from 3 back to 1. Here, from 4 to 2. There are some rules here, like I can, because like theoretically, right, I could write this in a different way. So note the notation like 5, 4, 2, 3, 1 denotes the same permutation. So 3 goes to 1, 1 goes to 3. That's really the same thing as 1 going to 3, 3 going to 1. Here, 5 goes to 4, 4 goes to 2, 2 goes to 5. That's the same thing going on here. These two are the same. So this isn't great because I want this notation, this cycle notation, to be unique so that it can help me with these counting issues, right? I don't have to worry about, oh God, like non-unique representation of these things. So what do I require? So 1, the cycle containing 1 must appear first. So this must appear first, followed by the cycle containing the smallest number not appearing in the first cycle. So followed by the cycle containing the smallest number not appearing in the first cycle, and so on. So the third cycle will be the one that contains the smallest number not appearing in either of the first 2 cycles, and so on. Okay, and the second requirement is that the first number listed in each cycle should be the smallest number in that cycle. So it should be the smallest number in that cycle. Okay. Now, here's a quick question. What if pi of I is equal to I for some I? So what if the permutation fixes a position, fixes an object? So here's a quick example. Let's say pi of 1 is 2, pi of 2 is 3, pi of 3 is 5, pi of 4 is 4, and pi of 5 is 1. Okay. What would this look like in cycle notation? In cycle notation, I'm going to start with 1. 1 gets sent to 2. 2 gets sent to 3. 3 gets sent to 5. And 5 gets sent to 1. So I close that cycle. 4 gets sent to itself. It is a 1 cycle off by itself. So the way that we do this is that we typically omit these 1 cycles. So that it is taken as a given if you are looking at permutations in, say, S5, as this object is, that if you have in cycle notation listed this thing, it is understood that it fixes 4. Even though 4 doesn't show up, anything not showing up here, if you have letters for it, gets fixed. So if you're doing this on 10 objects, everything besides 1, 2, 3, and 5 get fixed. So 4 gets sent to 4, 6 gets sent to 6, 7 gets sent to 7, and so on. Anything not showing up in the cycle notation is fixed. Okay. What about the identity notation? So what is cycle notation for the identity element of Sn? Because if we're omitting one cycles, the identity element of Sn fixes everything. So this fixes every object, i.e. pi of I is equal to I for all I, right? If I'm omitting all the one cycles, I would omit everything here. So the way that this is written typically is the single one cycle 1. It's understood there that this is the permutation that fixes every object. It fixes 1, and all the others don't show up. 2, 3, 4, 5, and 6, 7, and so on don't show up, so they can be assumed to be fixed. Okay, in this same way. Okay. So now, what was the purpose of this? The purpose is to make it easier to multiply. Remember, this actually means compose two permutations. So let's do an example. Okay, so say that we're in, let's let pi 1 and so pi sub 1, pi sub 2 be elements of the symmetric group on 5 objects. We'll let pi sub 1 be the, in cycle notation, 1, 3, 2, 5, 4. And we'll let pi sub 2 be 1 long cycle, 1, 5, 4, 2, 3. And let's compute their product, right? This is their product in S sub 5. It's a composition. Because it's a composition, again, this is read right to left, right? So this is right to left here because this is function composition. So writing them in cycle notation, I could put the circle here, but I'm actually just going to put okay, I'll write it, whatever. How do I come up with what this is? Well, it turns out that if I follow the rules here, what I get, my answer is in cycle notation. Okay, so this becomes a really convenient way for coming up with examples of these things and also for actually computing with these things. So how does this work? I'm starting on the right here and I say 1 gets sent to 5. So then in the composition, I should see what 5 gets sent to. Well, 5 gets sent to 4. So I'm thinking in my head here, okay, I want to know what 1 gets sent to in this whole composition. Right to left. 1 gets sent to 5, but then in the composition, 5 gets sent to 4. So the ultimate result of this is that 1 gets sent to 4. Okay? If you don't understand that, pause the video, go back and rewatch this. This example is basically the full explanation for how cycle notation works. And when you understand exactly how this works, you'll be very comfortable computing with all this stuff. And this is, to really have an intuition for what's going on, you kind of have to grasp this stuff. So 1 gets sent to 4. Okay, but then what about 4? Well, 4 gets sent to 2. Right, so 4 gets sent to 2 here, but then 2 gets sent to 5. So here, that results in 4 getting sent to 5. Okay, 5 gets sent to 4 on the right, but then on the left, 4 gets sent to 2. So that results in 5 getting sent to 2. Here, 2 gets sent to 3. And on the left, 3 gets sent to 1. So that results in 2 getting sent to 1. So I close this cycle. And 3 is going to get sent to itself, but I can just verify that if I don't believe these previous computations. So here on the right, 3 gets sent to 1. And on the left, 1 gets sent to 3. So that results in 3 getting sent to 3. So you could write this with a 1 cycle, 3 gets sent to itself, or write it omitting that 1 cycle. And there we go. Okay. Now I want you to check what if we do pi sub 2 composed with pi sub 1. Rewriting this is 1, 5, 4, 2, 3 composed with 1, 3, 2, 5, 4. So again, I'm going to start with 1 here. 1 gets sent to 3, and 3 gets sent to 1 on the left. So 1 gets sent to 3, 3 gets sent to 1. So this results in 1 getting sent to 1. And I start a new cycle. 2. 2 gets sent to 5. 5 gets sent to 4. So 2 gets sent to 4. Okay. 4 gets sent to 2. 2 gets sent to 3. So 4 gets sent to 3. 3 gets sent to 1. 1 gets sent to 5. And just to check that this actually closes up here, 5 gets sent to 4, and 4 gets sent to 2. So 5 gets sent to 2. And that closes up. So this is 2, 4, 3, 5. Notice these two are not the same. This shouldn't be shocking at all. Of course, you know that function composition is not commutative generally. So this means that in general, S of n is not commutative. Or I should say is not abelian. Which means this group operation here is not commutative. And that is to be expected in the general case. Okay, I have a couple very specific groups that I will talk about next time. So we'll start there. All of this is building up to the big enumeration theorem. So we're going to use Burnside's lemma to answer some of these questions, and then we're going to talk about a generalization of Burnside's lemma to a more general enumeration question that is going to yield answers to all these things we originally started with. So these original questions we had, like, how many seating arrangements around the round table King Arthur and his knights can I form? Or how many of these colored beaded necklaces can I form, taking into account the symmetry? Okay, so this is where we will start on Monday. So so we're finishing out some stuff. Like I said, once we talk about applications of this stuff, I wanted to talk about a couple other types of combinatorial numbers that show up, and then that will pretty much be the end of the course. So we got next week, and then that's it. That's everything. So anyway, I think I'll stop here for today. I will see you all on Monday.